a universe of seemingly infinite scale and countless wonders, it's curious that the one thing we are hunting for most is ourselves. We are desperate to discover that we are not alone. Just 40 light-years away, in the constellation of Aquarius, lies a tiny, dim star, TRAPPIST-1e. It's cold, ancient, and barely visible. And yet, it hosts something extraordinary. Not one, but 7 Earth-sized planets. It's as if nature itself set up an experiment. Can life exist around a star like this? One by one, scientists have ruled out most of these worlds as being habitable. Too hot, too cold, no atmosphere, no chance. But one world still holds promise, TRAPPIST-1e. And now, thanks to data from the James Webb Space Telescope, we may finally have a glimpse of its atmosphere. What we found is astonishing. Could this be the first true Earth-like planet beyond our solar system? Could TRAPPIST-1e host life? Join me today as we travel to the TRAPPIST-1e star system to explore the potential for life on its most promising planet. We'll look at new data from the James Webb Space Telescope, data that has pushed the observatory to its absolute limit, revealing the likely composition of TRAPPIST-1e's atmosphere and whether it could support life. That is, if the very star that offers the chance of life hasn't also issued a death sentence. TRAPPIST-1e is an M8 class red dwarf, only a little larger than Jupiter. It's 1,800 times less luminous than our Sun. That's the difference between a single candle and a stadium floodlight. Although the star was first discovered in 1999, its full planetary lineup wasn't revealed until 2017, when it became the first and only planetary system to be discovered by the TRAPPIST Optical Robotic Telescope. This telescope is actually made of 2 parts, TRAPPIST South in the Chilean mountains and TRAPPIST North in Morocco's Atlas Mountains. They use a technique called transit photometry. This method measures periodic changes in the brightness of a star to find orbiting planets. In other words, if a planet passes between us and its star, some of the star's light is blocked, and we detect a dip in its brightness. By taking multiple observations, the telescopes were able to isolate the individual orbits of multiple planets around TRAPPIST-1e. Initially, their data analysis only found the 3 innermost planets. But further data from both TRAPPIST telescopes, as well as the Spitzer Infrared Space Telescope, took this total to 7. And not only that, they are all rocky, and all, at least roughly, Earth-sized. This makes it the system with the most Earth-sized planets ever found around a single star. If you'd like to know more about all the individual planets around TRAPPIST-1e, I made a video about them. You can check it out at the link on screen. But with such a small, dim star at the center, is there really any hope that they could be habitable? For any of these planets to receive enough light to support life, their orbits need to be much closer than we are to our Sun. And in the TRAPPIST-1e system, they certainly are. In fact, all 7 are incredibly close. TRAPPIST-1e orbits at only 1/13 of Mercury's orbit. This means it is almost certainly tidally locked to its host star, the same side of the planet facing the star at all times, just like we only ever see one side of our own moon. This tidal lock has significant implications for the planet's habitability, and we'll dive into those later in the video. But here's the exciting part. Its orbital distance puts it right in the middle of the predicted habitable zone. This is the Goldilocks region where it receives about 2/3 of the energy that Earth gets from our Sun. That is why scientists are so curious about this specific planet. But it takes more than just light and warmth for life to thrive. TRAPPIST-1e would almost certainly need an atmosphere. So that's exactly what scientists have been looking for, using our most powerful space-based observatory, the James Webb Space Telescope. Now, the teams who were involved in developing James Webb were rewarded with guaranteed observation time. One group, the deep reconnaissance of exoplanet atmospheres through multi-instrument spectroscopy, or the much cooler Dreams team, immediately wanted to set Webb's sights on the TRAPPIST-1e system. The James Webb Telescope is uniquely sensitive. It's so precise that it can detect the faint chemical signatures from the thin band of gas, an atmosphere, on a planet 40 light-years away. It does this thanks to a technique called transmission spectroscopy. Here's how it works. As the exoplanet passes in front of its star, Webb doesn't just measure the drop in brightness, it measures how the spectrum of the starlight changes as it filters through the planet's atmosphere. The telescope's NIR spec instrument measures infrared wavelengths. Different molecules in an atmosphere, like methane or carbon dioxide, absorb very specific wavelengths of this light. They leave behind a unique chemical barcode. By measuring which wavelengths are absorbed, we can first work out if there is an atmosphere and, second, what gases are present. And here's a lucky break. It's been particularly easy, by astronomical standards, to get a read on TRAPPIST-1. In fact, the data we have is 10 times more sensitive than what we have on almost any other system. Why? Counterintuitively, it's because the star is so dim. Think about it. An Earth-sized planet blocking a tiny, dim star causes a much bigger relative drop in brightness than the same planet passing in front of a huge, bright star. A bigger difference is easier to measure. Using these measurements, the team has already discounted TRAPPIST-1c and 1d from having atmospheres. But the results from TRAPPIST-1e, a rocky planet about 90% the size of Earth, were so intriguing that scientists couldn't ignore them. It looked like this planet might, in fact, have an atmosphere. This was more than enough evidence for the DREAMS team to decide to use up all of their guaranteed JWST time trying to find out more. So far, they have observed 4 separate transits of TRAPPIST-1e with James Webb. So what did they find? Well, we can start by discounting a few possibilities. We now know that TRAPPIST-1e does not have a primordial atmosphere, the thick, gassy envelope a planet is born with. These are usually dominated by light gases like helium and hydrogen, which haven't been detected. They were likely stripped away by the star's fierce radiation long ago in its life. Nor does it seem to have a thick, dense, carbon dioxide-dominant atmosphere like Venus. And based on the recent measurements, a thin, sparse atmosphere like that of Mars is also unlikely. Believe it or not, all of this is good news. It's unlikely that any of those atmospheres could support life. Well, not as we know it anyway. So, what atmosphere does it have? Well, here's the big one. There could be an Earth-like atmosphere. We're talking about one dominated by a heavier gas, such as nitrogen, with a strong greenhouse effect from water, carbon dioxide, or methane. An atmosphere like this, with a surface pressure of around 1 bar, equivalent to Earth's, may be able to sustain enough heat transfer to the dark side of the planet to allow for a global surface ocean, despite it being tidally locked. Were this confirmed, it would make headlines the world over. However, that might be too much to ask. The data, right now, instead slightly favors the idea that TRAPPIST-1e is a cold planet without a global ocean. Analyzing the data correctly here is absolutely key. Being able to understand what we're seeing and what it means is the difference between the discovery of the century and an embarrassing mistake. Now, let's get back to TRAPPIST-1e. As I mentioned, there is an alternative to an Earth-like atmosphere. High levels of methane could instead create a reverse greenhouse effect. You see, TRAPPIST-1 is much cooler than our Sun, and more of its energy is in the near-infrared wavelengths. Atmospheric methane is great at absorbing that specific energy before it even reaches the surface, then re-emitting it back into space. The result? A cooler atmosphere. For the tidally locked TRAPPIST-1e, this would mean that liquid water might only exist on the surface of the planet that permanently faces the star. No global ocean. But that's not necessarily bad news for life. Either, such conditions could satisfy Darwin's warm little pond hypothesis for the origin of life. And atmospheric modeling has backed this up. Simulations suggest that even if TRAPPIST-1e has limited water, or if that water is locked on the dark side, it could still have a stable atmosphere. This might lead to what's known as Terminator habitability, where life could only find a home in the dynamic band of perpetual twilight that separates day from night. But water on the surface isn't the only option. We know TRAPPIST-1e is rocky, but not much more. It may be an icy, volcanic planet with a subsurface ocean, just like we find on Europa and Enceladus in our own solar system. Life on Earth is believed by some to have formed near deep-sea vents, and the same process could happen on 1e. No matter where on TRAPPIST-1e water may be, life is possible. There's an energy source and, potentially, an atmosphere that provides the building blocks for life. But there is one massive issue. Although all these things are possible, scientists still can't completely rule out the possibility that TRAPPIST-1e is just a cold, barren, airless marble with no atmosphere at all. So, we need to talk about what could prevent a stable atmosphere from ever forming. And in this case, it's the red dwarf star, TRAPPIST-1 itself. Imagine standing with me on TRAPPIST-1e just for a second. Look up. The star above us would appear more than 4 times as large as our sun in the sky. It would be a deep red-orange color, illuminating the sky as if in perpetual sunset. What a sight that would be. Now, red dwarfs are extremely active. They produce more powerful flares than our sun, and more often. The worst recorded geomagnetic storm ever to hit Earth was the Carrington event in 1859, a greater than 1 inch to 100-year event. TRAPPIST TRAPPIST-1 is believed to release a flare that powerful more than once every 2 days. You'd likely be able to watch solar flares arcing out into space in real time. And they carry huge amounts of energy towards the planet, enough that over time, any atmosphere could be stripped away, making life as we know it all but impossible. That's assuming the atmosphere was ever allowed to form at all. Red dwarfs are stupendously long-lived. TRAPPIST-1 is expected to exist for 10 trillion more years. That is 700 times the current age of the universe. By comparison, our sun likely only has 5 billion years left. You might think, given that stability and lifespan, there would be plenty of time for life to find a way. But because of their long lives, their chaotic and energetic teenage years are correspondingly longer. It's during these formative years that planets should be producing their own atmosphere, replacing their primordial one with heavier gases like carbon dioxide, nitrogen, and methane released through volcanic activity. The problem is, if the star's aggressive, atmosphere-stripping phase lasts too long, an Earth-sized planet might not have enough resources in its interior to ever generate a stable, life-supporting secondary atmosphere. The unfortunate reality is that if a planet's atmosphere isn't established before 5 billion years, it may never generate one, condemning the planet to a death sentence before it was ever allowed to live. I know, it's actually sounding rather hopeless for TRAPPIST-1e, and I bet you're wondering, how is this one of the most promising planets? But we don't yet know, one way or the other. We've already seen there are hints of an atmosphere's existence. And although the star's violent outbursts may be 1e's downfall, they may also be completely necessary for life to begin. UV radiation from flares may be essential to create RNA building blocks, molecules central to the metabolism of every life form ever found. And now that TRAPPIST-1 is in its calmer, main sequence phase, there is a chance for a stable, habitable atmosphere to exist. And that atmosphere could have protection, its own magnetic field, just like Earth's. The Earth's magnetic field exists because of its moving, molten outer core. There is a good chance TRAPPIST-1e has a similar system. In fact, 1e's close orbit could help maintain its magnetic field. If its orbit is eccentric, not perfectly circular, this would cause repeated compression and relaxation of the planet's shape. This process creates internal friction that could heat the interior, much like we see on Jupiter's moon, Io. Io is tidally locked with an eccentric orbit, and it gets stretched and squashed by the other moons, pumping it full of energy and making it the most volcanically active body in the solar system. So where does this leave us? Well, we may have an Earth-sized, volcanically active, rocky planet with the building blocks for life, its own atmosphere, and a magnetic field, orbiting in the habitable zone of a relatively calm red dwarf. Or it could be a cold, dead world. So let us know in the comments which scenario you think will eventually be confirmed. We might not get an answer until the proposed Habitable Worlds Observatory launches in 2041, but until then, James Webb's observations are our best bet. The fact that we are able to measure the light absorbed by a thin gaseous layer around a rocky planet, orbiting a dim red dwarf star 40 light-years away, is pretty incredible. And scientists haven't given up. They've learned from the first sets of James Webb data and modified their technique. With another 15 transit observations planned before December, they expect to be able to confirm the presence or absence of carbon dioxide in a secondary atmosphere, a key step in the search for life on 1e. Perhaps TRAPPIST-1e and its neighbors will turn out to have a unique, inhospitable atmosphere, or perhaps one that could theoretically support life. Or maybe, just maybe, we'll find one just like home. It's exciting to find so much potential for life relatively nearby, even in the midst of an extreme environment. But whatever the atmosphere turns out to be on TRAPPIST-1e, I find it hard to shake the feeling that the discovery of extraterrestrial life feels inevitable. The only question is, when?